Yeah, working in PVH Europe, so you don't know this company for sure, but you know Tommy Hilfiger and Calvin Klein, so I'm kind of fashion guy. You don't see it by my outfit, of course, but I tried best with best stuff I have. Yeah, so today we'll talk about guided generative adversarial neural networks. It's kind of a subclass of adversarial neural networks. There are a lot of them, and we created one extra name in this field, so we create extra confusion. Yeah, thanks for us for that. Agenda for today. So we'll start with some overview. We'll build up knowledge about that field. Probably not everybody knows what is that about. And then we'll stop for the live demo, because I'm kind of practitioner. I don't like the only theoretical stuff. So the live demo will be right in the middle. We'll see how, not how it works, but it works. And then we'll look to the architecture and understand how it's implemented. And then at the end, super new slides, and I just added them yesterday. It's extra stuff for those who will sit till the end of the session. You'll see how to combine toilet seats and fashion stuff. Kind of excitement, I hope it's created. So let's go. Overview, neural networks. I have to start with that stuff to understand your level, guys. Everybody knows what is neural network. Raise a hand. Yee. Okay, all right. Convolutional neural networks. Raise a hand. Cool. Deconvolutional neural networks. Okay, if you're a posh data scientist, then transposed convolutional, if you know that name. Okay, so I have to start with that part. Convolutional, deconvolutional neural networks is like Chinese convolution. So if you read from right to left convolutional stuff, then you have deconvolutional neural network. In convolutional neural network, you get an image, and then you convolve this image to vector or to digit. Like in that case, you convolve image that recognizes that there is a cat on the image to just category 1, it's a cat, 0 is not a cat. And the convolutional neural network does totally the same job, but reversed. If it's 0 in the input, then it gives you something but cat. And if it's 1, then it generates a cat. So simple as that. So how it works, it's a different question, and we will see that later on. Of course, like how many cats can you generate from digit 1? Like a lot of. But there is a way how you can do that. Then autoencoder, it's a combination of both. Like it's convolutional and deconvolutional neural networks stacked together. You have an image, and then from image you produce an image, and it sounds like it makes no sense, but of course it makes. You can consider autoencoders like a compressor. So you have an image that you compress that into, in that case, 0, 1, cat, not cat, so you can store just 1 byte of the image, and that is the entire image. You can kind of compress the image in a lot of times, and then from this category you store the image back. Probably with loss of quality, but yeah, still. All right. Generative models. So what do we mean by generative models? First of all, what is non-generative model? Like what is the normal model? Like normal model is, in that case, we have a spam classifier that classifies if an email is spam or not spam, and the information about the fact that the email is spam is implied there. So we just extract the information. We don't generate any new information. It's already stored there. And generative models is the opposite situation when we have like the space of the lower dimension, then we have transformation to the higher dimension space. When from like some small object, we can generate a bigger object. So we just put some noise, for instance, in generative model, and it generates random email. So that's kind of generative model. It generates new data for us. Then the stuff we'll talk about later, but related to images, so it's not an image stuff yet. Well, it's guided generative model. It's a generative model with some guidance. So we would like not only generate random emails, we'd like to put some message inside. So we'd like to say, hey, like we generate a message with email with the fact that you won 20 million euro, and then to get this money, you have to transfer $5 to my Russian account, for instance. So you put the information back, then you generate the entire email text, and yeah, with clear message inside. The next, generative adversarial networks, and now cool stuff begins. Anybody knows what is generative adversarial networks are? Wow, amazing. So I don't need to explain in details. 2 pictures on the slide. Like picture on the top is like photos. It seems to be photos of bedrooms. It's a famous data set, but all of these pictures are not photos. They're fully generated. So this type of architecture can generate new stuff that looks like the data set, train set, but never existed in this train set before. And then the picture below, it's, what's that? It's kind of level of 8-bit game, and this game never existed. It's also generated from nothing. It looks to different levels of 8-bit games, and then from then generate a totally new stuff. how it works. So that's the crucial thing to understand the guided generative adversarial networks. I will shorten that to gens, okay? So how gens works. Actually, gen is a game between two parts. So we have two neural networks inside, generator and discriminator. And generator does only one thing. It generates you images from noise. Like you press the button, like you start the training process, noise go to generator, generate something, like some image. Of course, at the beginning it's noise, it's pure random pixels. The second neural network, discriminator, looks to this image and tries to recognize if this image is generated or real image. How it works, it has two samples actually. One came from generator, one picked up from the train set. So first of all, discriminator, of course, just guess randomly which one is fake, which is not fake. So it says, okay, the image above it's real one, the image below it's fake one, it's good, and then the loss functions go down for discriminator. So discriminator is just classifier that says if image is generated or not generated. If discriminator is okay, so discriminator make a right choice, then we penalize generator. We say to the generator, no, it was like a bad image, generate something better. And then generator generates something better. And then discriminator discriminates better. And then they play with each other. You like, I don't know, go on vacation, after 8 days you come back, and then you see fully trained neural network without any efforts. So like computer, trained computer. Yeah, how it works, you have two loss functions, and should I go to that details? To some mess stuff? Not really? Yeah? All right. So is fake is if image is fake, should be 0 in the right case. Is real should be 1 in the right case. So for discriminator, if fake is 0, then logarithm from 1 is 0, and if it's real is 1, then logarithm is 0. So it's ideal situation. The discriminator gave a right answer. The opposite situation, these laws go to infinity, and then it's bad. And how do they connect to each other? We are reversed generative part of the loss of discriminator. So generator tries to create such an images which discriminator estimates like a real images. Yeah. So if it's fake, it's 1, then loss of generator is 0. So ideal situation. If discriminator says yes, it's fake, so it's 0, then log goes to infinity, then it's bad. And they play with each other and generate such images you saw on the previous slide. Generator, in that case, is just the convolutional neural network, and discriminator is just simple convolutional neural network. It's vanilla stuff. If you try to implement it in one day, you've done it, it will work for sure. But with some exceptions, but we will see later on. Next type. So that was the starting point for our research. It's conditional generative models. Oops. Pardon. What is conditional generative models? On the previous slide, you saw that we put noise to generator. So the generator starts from scratch. It gets some random vector and generates the image. But what if we put some image to generator first? So generator, in that case, is not only the convolutional neural network, it convolves some image and then deconvolves it back. For instance, in that way, you can colorize images. So your input is grayscale, your output is fully colorized image, and yeah, the stuff will do the job. Or like Google create Google Maps, for instance, you have a photo from satellite, and then just photo from satellite you translate to the map. Yeah, all right. Or yeah, actually, this project was the starting point for our project, where you translate edges to the real object, like to fully detailed design. But the difference between guided generative models, and we'll see that later, and conditional is in the fact that in conditional, we have very strong condition. So if you look that these edges are not, like it's not a sketch. It's just edge detection applied on the output, and then by these edges we restore output. Or grayscale image, just 100% connection between grayscale version and fully colored version. If you grayscale the output, then you have an input. So they're strongly connected to each other. In our approach in guided, we don't have strong connection. We say that the output should inherit some properties of the input, but they should be disconnected. One other application of conditional generative models is, it's very funny by the way, these 4 phones, they have totally the same sensor. So the same Sony Exmor RS camera thing. But Google Pixel is much better than the rest. And Google Pixel was the best camera phone of the previous year, and Google Pixel 2 is the best camera phone this year. So why? And answer is software, of course, probably is the corporate secret of Google, but yeah, they admit that they use neural networks for the image processing. Probably what do? They use so-called super resolution architecture, which is based on conditional neural networks, which restores the resolution. Like from the low resolution, you can restore high resolution. As the human being, you can do the same. Like if you look to the window, like pixelized window, you understand that it's window. And if I would ask you, like, how would you draw this window, then you can do that because you saw so much windows before. The same you can do with neural networks. Like you train on different pictures, and of course, Google has an enormous database. So they can train their systems to restore resolution of the image even without having good hardware. And then the problem we solved. Like I said before, we work in fashion industry. And in the fashion industry, there is a huge gap between the process, between the time when designers started to design clothes and they reach shops. It can take like 1.5 years from the very beginning till the sales process. And of course, you would like to be trendy. Like you would like to understand what you are selling now or what will be trendy in future at least. So you have to know your customer as good as you can do that. And how can you make research? Surveys, but like people are not that honest with given questions, or building such a thing. And what we did is we created a website, and on this website you can just draw some sketch with few colors. Then you can press one button, make this sketch the fully detailed design, and it does the job. Yep. Has anybody heard about deep style? Yep. The big difference between deep style and guided gens is the fact that deep style relies on the quality. If you provide low quality image as the input, then you get bad quality as the output. In our case, like crap is welcome. You just put some random sketch inside, and we guarantee that the right answer, like right quality, will be in the output. The same about style. We'll see like why there is a styles in the architecture as well. In deep style, you have to have a good style. If I don't know, you extract some style of my paintings, of course, it will be like random stuff in the output. But the most important thing is there are some architecture of deep style when with one feed-forward propagation you can generate images. But if you change the style, then you have to retrain the entire network, and it will take hours and hours and hours. In our case, everything is on fly. So you provide different styles and different sketches, and it mixed together, yeah, like in one feed-forward propagation. Live demo. Here we go. So that's the website. You can draw some sketches and get the stuff at the right side. So the stuff at the right side is fully generated. There is nothing to do with like resizing, reshaping things. It's like pixel-wise generated objects. There is a slider. You can ask the system generate something that looks more real or it looks more like a sketch. And it's done because user complained at the beginning. There is always a trade-off. You would like to stick to a sketch, then you lose like small details. You lose wrinkles, you lose like small patterns. If you stick more to realistic looking design, then of course not all details from sketch will be taken over. So that's why we gave a flexibility to choose like where would you like to go, to robot size or human size. Then at the same time, by the sketch we understand what is shown, and according what is shown, we select a style to combine the sketch with. To prove that it's fully generated, let me introduce more randomness, like a bit more. If you look to wrinkles, they will move around. So, yeah, it's not that amazing from user perspective, but from technical perspective, it proves like it generates stuff from scratch. So it's really not reshaping, resizing stuff. All the wrinkles are generated on the fly. Yeah, if I draw something else, I don't know, like colorize this thing, please. Yeah, then it'll be colorized. We're going a bit more to sketch side. Change the color. Red. I don't care about the quality so much. And if it will be deployed, like if management will approve that we'll roll out the system globally, then of course, like you have to, consumer will not invest more than like 1 minute on this website. If you ask to draw like high quality sketch, nobody will do that. So it should be quick and dirty. I don't know, blue. Okay, if you don't like that, you press I don't like that. Then computer is very sorry, and we'll start generating the new stuff. All right, so you see that this version is a bit blurry, partially because I introduced so much mess, so much random noise inside the model. So yeah, now it's a bit better, but not ideal, because it's work in progress, and yesterday I got new training results from the model, which are much better than before, with like better details taken over from Sketch, like better resized and so on. Now it doesn't copy details like one-to-one, it also tolerates like rotations, like shifts around and so on. So then how it works? First of all, we hired 20 students to draw sketches. Of course, you need to prepare a data set, so we hired some cheap labor, and about 3,000 of sketches were drawn by students, like 3,000 pairs, real design sketch. And then from those, we generated about 200K data points. Of course, with the simple like swap shifts and transposition of the images, like rotations and so on. But the most important in that case is color shifts and color swaps. And if you have the same data sets, don't forget about that. Like if you look to, do you have a mouse here? Yeah, cool. So look at this hoodie is red, and if we just swap two color channels from red to blue, then we have blue hoodie and nothing changed. Of course, neural network will learn like how to interpret different colors, but blue hoodie and red hoodie, they can exist. So we argument data in a lot of times in that way. Then the architecture of the solution. So starting point gen, not that interesting. Actually, the actual starting point was conditional gens. Again, like I said before, the biggest difference between conditional gens and guided adversarial neural networks is in the fact that in that situation, in conditional situation, our input is just edge detection of the output, so they're strongly related to each other. And of course, the first logical step is, okay, we provide a sketch as the input, so we disconnect output and the input. And actually, like, it's done because that is what you need, but of course, in practice, it doesn't work. Maybe it will work if you have like million images, but yeah, who has this type of data? So what we did as the second step is we introduced the second loss. So now we have 3 targets already. So we have discriminator target, so that image should look real. Then the second, it should be similar to the style, And then it should be similar to resized and reshaped sketch. So we don't want to lose the form. So we got all the sketches, we resized them as the actual image, we reshaped them, and we said, okay, like the output should be similar to that as well. Why? Because if you draw the line on the sketch, you would like to see that the system draw the line on the output as well. Otherwise, it's confusing. Like you draw the line and nothing happened. All right. Then what has been done as the last change in the architecture, we feed input to the output. It's kind of forbidden stuff, but sometimes it's possible. So we got the real image. We feed this image to extra convolutional neural network, and then the output of this convolutional neural network, like the last in layers, we inject it into the deconvolutional part of generator. So effectively, what it's doing is extracting features of the style, like it's compressing images, it's getting the most important things to restore the same image back. Like it ignores all the small, like I don't know, shadows, like small wrinkles. It really tries to extract the most important stuff, and then by this most important stuff, it restores the image back. So what is happening is like, this convolutional neural network of autoencoder, so generator extract features of sketch. This convolutional neural network extracts features of output, like of style, and then their features are injected to decoder, and then decoder reconstructs the entire image back. So that's why it's not like applying styles. It's really extracting features from images, like lines, shapes, colors, and then from list of features, we recreate the image. And how we create image? With generated adversarial neural networks. We also introduced new terminology, position maps. I am really careful saying new because at least we haven't found anything in the literature. So that's why we call it position maps. We'll talk about later, just not forget about them. We'll come back to them. And one addition into generator architecture, in between we also have one fully connected layer to understand what is drawn on the sketch to find the appropriate style later. Like if it's short sleeves, long sleeve, there is color, buttons, and so on. Yeah, as I said, actually deconvolutional neural network is not like simple deconvolutional neural network. At some point it splits into 4 parts to generate 4 different images. One is most similar to style, another is most similar to input, and like 2 of them in between. Yeah, to have this balance, like to give an opportunity for user to choose what is needed. Again, to prove that it's not copying of the style, it's really extracting of the features. If you look carefully to the style, you see that wrinkles are on the different places. Like there are buttons, there is no buttons, color is different, like color of the color is different as well. Like, just basic features are extracted, like shape, yeah, maybe some stuff, like maybe the position of wrinkles, where do they point, but the image is generated from scratch, like from the details extracted from both. Discriminator, very easy stuff, it's just page can. Like it's almost the same like just deconvolution neural network, but it doesn't convolve to the 1 or 0 if it's real, not real. It convolves to some certain point where we regionally can say, okay, this region looks like a real image, but another region doesn't look like a real image. So it also points like, okay, here something should be improved. So it's not like only real one, not real one, but if it's real one, then here, here, here. Here, it doesn't look like good. Loss functions. So gen loss we already seen before, just classic gen loss. For a comparison with sketch and style, there is one extra thing has been done. So usually in literature you'll just see L1 loss, just pixel by pixel subtract images, take the absolute value from them, you're done. What we did, we also introduced extra addition. So red graph is our loss function, classic one is blue. Our loss function behaves totally the same like L1, near the 0, like if images are close to each other already, then it's just L1. But if they are so different, then we penalize it very hard. And why it's needed? Because we have background. And maybe in the similar problems, you will have the similar problem. You'll have some background color, and the easiest solution for the neural network is just generate white images all the time. It's always a solution. So to penalize so different images, we introduced the extra addition here. Then the similarity to the style. First of all, it's just one part of this similarity, one part of loss function is our log t of both, of the generated output and the style. And the second part is edges. So what do? We extract edges from the style, and then we say that edges should be the same. Why it's important? Because like pattern, doesn't matter which color pattern has, like a big H, Tommy Hilfiger thing. You would like to preserve edge in the output image. So you'd like to have edges, but maybe not color. Yeah, so you can extract edges on the fly in TensorFlow. Actually, just grayscaling of the image first, then you apply max pool, and then you subtract from the original max pooled image. And yeah, you have to scale that from -1 to 1, in our case at least. Then you have edges. So yeah, we put extra addition to a loss function, then we have like, emphasized that edges should be the same. For the style, we do the same. Also, just not really. It's because it changed. Sorry to say that because we always change the architecture, and I think that was introduced 1 week ago. So what do is when we compare style and the output, then we compare not image pixel-wise, but only in places where contrast is changing. So again, edges, but not solid spaces. Because if you compare pixel-wise, like here we have white space without any wrinkles. And if you just subtract from the output this white space, then you vanish these wrinkles from the output image. So you penalize having verity in the solid part of the image. So we don't do that. We just extract parts of the image where edges are, and then subtract one image from another only in the parts where edges are. And the second part is, but still, if, for instance, the entire image is colored in red, then we would like to have a red image as the output. So we resize these images in 16 times, and then we compare pixel-wise resized image. And small differences are gone, but color, like main color, is preserved. Training process, like, okay, some extra demonstration. First of all, after minutes, it picks up sketch immediately and reproduce it in kind of decent quality. After a few minutes, it picks up style, also pretty quick. And only after hours and hours and hours and hours, it refines the details. So that gen part comes into play as the last step. Yeah, so let's watch a video. That's how it goes. So yeah, sketch is already there. Then the color from the style starting to appear, and wrinkles already somewhere, but not really. And probably like 30 seconds from now, it will be just blinking, 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 adding details, like refining the edges, refine the shapes, and so on. It's not the best model, by the way, because you see on the left bottom, right bottom view image, there was some stuff around the image appearance, so it's kind of, yeah, problem. And there you go, I think it's already stabilized. Yep. Right, then position maps. You remember I said, like, keep in mind, position maps, we'll come back later to them. What is that? If you go to the original paper of conditional adversarial neural networks, they, as I said, they use as input just edges of the output, and then by edges, they restore the image. So what will happen if you just draw eyes on leg of a cat? Yeah, well, then you have eyes on leg of a cat. So it doesn't really extract features of the image. It just sees, okay, some rounded things should be eyes, and that's it. And why is it happening? Because by default, like by design, convolutional neural networks are position independent. Like on this image, you have cats, 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 cats. Like this cat, 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 and behind them is also cat. It doesn't matter where cat is. Like if it's see the head of cat, then it's cat. Great. But in our case, like white can be background, and white can be color. And the system should understand that white can be different, depends from the position of white. Like probably in upper position, like here, and if it's surrounded by something, then it's not background already, it's color. So I have to put white color. And how it's done, very easy trick, by the way, but we haven't found anything in the internet. You just, as the feature map, you provide like images, and the images inside you just put figures 1, 2, 3, 4, 5 that define the coordinates of the pixel. So if among all the feature maps you also provide these two guys, then by having this pixel and that pixel, the color of them, you know where you are, like just X, Y position. In principle, it should work. In practice, you have to provide like extra feature maps, position maps, sorry, because your learning rate is too low for that. So then you have to define your coordinates, like you have something base, something like you have not only like 1, 2, 3, 4, 5, but 1,000, 100, 10, for instance. So you provide 1,000 as the separate feature map, and this kind of 1,000 base, and this is 100 base, and this is like 10 base. So to define the coordinates better. But this simple trick, and it worked perfectly. Mode collapse problem. So if you'll somebody tried to create gens, like generate images, or you just heard about them in theory? Nobody tried to? Yeah? And have you seen that situation when your mode were collapsed?
Especially in Cypher that we tried to generate.
Yeah? Then only one image all the time, right? So that's the well-known problem, and gens are well-known because of that. They're super unstable. And what you usually see, you start the training process, you see a lot of variations in the output images, you think, oh, so good. But then at some point it collapses and starts to produce you like one image or a combination of like 10 patterns altogether. So this one, for instance, is just simple gen trained on t-shirts, and you see that the variation is like nothing. All the patterns are the same, maybe like 5 patterns combined all together a lot of times. And that's mode collapse problem. Why it happens? Because if you look back to the architecture of the entire thing, there is no penalty if your output of generator is totally the same. Like generator can learn at some point of time, okay, I generated something that looks real, and discriminator says, yes, this looks real, and then it's stuck. So there is no any penalty saying you have to generate different stuff. That is why it's happening. If you go to the literature, last 2 years, there are a lot of papers that trying to overcome this problem. Like everybody is trying to solve it. we try different configurations, like different papers. Some of them are good, some of them slow down the entire training process. But one paper, I don't know how to pronounce the name of the guy, but they are really great. And what they said, you have to normalize weights. So they tried weight normalization for gens. Original paper of conditional neural network says that you have to normalize batch. So probably you know what batch normalization, right? Never. Like in that situation, never ever apply batch normalization. And the funny thing is that on the day one here, I heard from one guy, he said, always apply batch normalization for any problem. Nope. Because what happens when you apply batch normalization, you subtract mean, divide by variance, doesn't matter, but the most important is subtract mean, and you're averaging the data set. In our situation, for instance, we have batch of 2 images, like shorts, long sleeves, and short sleeves. And if you subtract mean, you're kind of averaging them together. You have some information from long sleeves mixed into short sleeves, and some information from short sleeves mixed into long sleeves. And that's why you'll start to have these blurry spots around. Even on the original, in the original work, they have this problem. I don't know why they recommended that. Probably they didn't research it well. But yeah, never. What works is instant normalization. So you can normalize, but not across the batch, across only one image. The problem will be if you normalize it like crazy. If you normalize all feature maps, then it will also stuck, because you decrease the variety of data immediately. So don't normalize if your feature map is smaller than 3.3. But the best one is weight normalization. Your weights are usually big, and you can easily normalize them. And weight normalization is a very easy trick. You just normalize weight and then multiply by some scale, which should be learned parameter, and plus beta, which is also learned parameter. So you have 2 extra learned parameters per each color channel or per each feature map, and that's it. The second finding they did is to use translated parametric value. They called it in that way. In gens, don't use don't use ReLU because there will be vanishing gradients problem. Use leaky ReLU, or the best one is parametric value. In parametric value, it's just leaky ReLU, where you don't freeze the scale. You just say, okay, it can be anything. Like you ask the neural network to find the negative scale of leaky ReLU. And yeah, like in all situations, don't use max pool because of the same problem, the vanishing gradients problem. Use average pool or stride more than one. It should be everything but, as I said, like some fun part at the end. What we did a few days back, and these slides were not in the original presentation, we decided, okay, this project is about fun, to be honest. Like there is no scope. Like the idea is to engage users, they come to the website, throw the stuff, and they enjoy it, they share it, and so on. And we decided, what if we introduce the forwards loss? So we have one loss that says that image should look real, another loss that image should look like a style, another loss that image should look like a sketch, and then one more loss is we pick up the output image, we put it through VGG16, and they say that on demand it should recognize some category on the output image. So we say like, on this t-shirt we would like to see toilet seat, or on this image we would like to see like aircraft carrier, or chicken, or horse, or cat, or I think it's axolotl. And it works. Like, we can create new patterns, like new patches on the actual designs. And the most funny thing is when I ask to create 2 categories, or 3 categories, or 4 categories at the same time. And then neural network starts to hallucinate with like some monsters. So probably this one, I know it's dog and like some flying eye. This dog and I think it's goldfish and train. This dog a cat. This one, I have really no idea what's that, to be honest, but this is kind of cool, right? Train and salamander, and this is kind of mess. Yeah, that's it. Thank you very much for your attention. I hope you enjoyed that. Yeah, if you have any questions.
Thank you. Thank you, Alexey. We've got some time for questioning. Yes, does anybody have a question?
So far, based on my study, one of the things that GAN is suffering is like quantitative and a metric of evaluation in terms of quantitative. Like most of the things that we are seeing is based on qualitative observations.
Yeah, principle in gens, there is no like metric saying if your output is good and bad, and it's hard to estimate like what is in the output. Usually, it's just you see with the UIs and you think, oh, okay, it's performing good. If it doesn't, then with your intuition, you have to fine-tune parameters, change the architecture. But yeah, there is no like standard way estimating if your gen is performing okay.
What you represent here is all of it art, design, something not realistic. It is creativity, some kind of. But do you think you can use such kind of network in estimate something in economy or in science or something real?
Well, it's generative neural network, so it's a different class. It usually doesn't make any estimations and generate new data for you. Well, and you said about designers. It's just one comment on that. Like usually people ask if this stuff will replace designers. And luckily this is tech conference and I can say yes, it will replace at some point.
This might seem a silly question, but you came up with the idea of the position maps to differentiate between the background and the outline of the T-shirt, right?
Yep.
Can you not just crop, because you did do edge detection, so can you just crop the T-shirt?
Well, I think the problem is different. Like here, do I have any example?
Because you're feeding the background to the neural network, can't you just crop it out and just feed where the information is?
Well, you are generating the entire image all the time, so you don't work with crops anyway. The output of generator is always the fixed size image, and in that image, do I have something? I should have. Oh, at the beginning it was, yeah, like here. Like the output image, like these small details will appear if the neural network knows like in which position is it situated. Because like, imagine that this color is white color, yeah? So when you convolve from the like inner layers of the convolution, with the convolutional neural network, then it doesn't know, because everything just colors, right? So all the pixels, it's just colors. And colors are digits, and digit of white to 55 to 55 to 55 is totally the same like the color thing. And if it can understand that I'm in that position, like my filter it should be activated here but not here, then it can put some extra details like that stuff there, but not just white space. Is it kind of answer? Because I didn't get it completely.
Yeah, I guess. Yeah, I was just wondering if, so you're basically keeping the size of the image the same and
Yes.
you're feeding the same size. I was just wondering if, is it possible to give a cropped image to a neural network, or you have to just keep always the same size?
I
for the
think
convolutions?
what you can suggest is why not to generate images by parts, like first part of network generates like this part of image, and next part of network generates this part of image, and then it's kind of focused on some part of image, not in the background if it's in the center, or on the background if it's in the corner, for instance. But I think then you can't merge them all together, so they won't fit.
Okay, thank you.
Because they will be all random. Yeah, it's all the random process.
Okay.
Right, do we have one more question? Or will that question come from me? Okay. Well, we've got two hands up, so okay. Since it's the last talk of the conference.
So I was just curious whether you tried generating the pictures with the models with the clothes on.
You mean the last night?
So if you fed it instead of just plain T-shirts, you would feed it people with the clothes on.
Oh yeah, yeah, of course. It doesn't matter. Like with this type of network, I hope we'll publish a paper at some point of time. But with this type of network, you can feed anything as the input. You can, I don't know, you can just put a clothes, the input, and train it to create people with clothes on. Yeah, of course, it will learn like with a relative big data set, with the relative big neural network size, because even that neural network size is 12 GB, so use batches 2. It's the maximum what we can afford on 12 GB GPUs. So it's the huge thing, but if you have enough data and if you have like large thing and you can parallelize the network across the serial GPUs, yeah, of course, you can address people with nil closes, or opposite if you want.
Hi there. Do you see this approach being used with audio or video in the future?
Yep. Yeah, definitely. And my example from the beginning with spam, I think, it's dark side of the process, but if you're working in a spam company, like try this architecture, like create spam that looks like real, so your discriminator will discriminate the output that it looks like a real email text. Your guided input will be like message you would like to provide, and yeah, generator will generate to spam that will penetrate the spam filter. And the funny stuff is you can constantly train that if your email is bounced, then you penalize the generator again, the generator generates new email, and then you go across the firewall through and so on, yeah. Or audio text, audio stuff, yeah, definitely.
Thank you.
But I think with audio you have to use RNNs, so I'm not sure that like plain architecture will help you. But yeah, just replace CNNs with RNNs, yeah, should work.
Hi, so here you were given an object like a t-shirt and you could sketch out a style and sort of generate t-shirts in that style. Do you think that you could also have a system where a user logs on and maybe selects 10 or 20 items that they might like in their wardrobe, and then that kind of aggregates some vectorized version of that style and then applies that to the t-shirt outline?
Yeah, that's a great idea, thank you. I'll try to do that.
I would like to ask a similar question. It does seem that your application has a lot of potential outside of its existing scope. Is that something you're aware of? And if so, what other possibilities are there?
Yeah, it's a good question. Like we have some idea for startups. Yeah, like it was the suggestion. You can provide any input and you have any output and as the output. So you can provide, I don't know, good idea was the dress and then have model as the output. Or on the website, you always use like photos of the people on clothes. So instead of paying for models, you can just put clothes in, press the button, and then model on this clothes will be generated, like smiling and staring some posture. Yeah, for instance, that.